Hello, this is Todd Booth. I'll be covering Chapter 8, which is Electronic Mail Security. In virtually all distributed environments, electronic mail is the most heavily used network-based application. Users expect to be able to and do send email to others who are connected directly or indirectly to the internet, regardless of the host operating system or communication suite. With the explosive reliance on email, there grows a demand for authentication and confidentiality services. Two schemes stand out as approaches that enjoy widespread use: Pretty Good Privacy, PGP, and S/MIME. Both are examined in this chapter. This chapter closes with a discussion of domain keys identified mail. And here's a quote. Go ahead and pause, read it, and continue. Pretty Good Privacy, PGP. PGP is a remarkable phenomenon, largely the effort of a single person, Phil Zimmermann. PGP provides a confidentiality and authentication service that can be used for electronic mail and file storage applications. In essence, Zimmermann has done the following. 1. Selected the best available cryptographic algorithms as building blocks. 2. Integrated these algorithms into a general-purpose application that is independent of operating system and processor, and that is based on a small set of easy-to-use commands. 3. Made the package and its documentation, including the source code, freely available via the internet, bulletin boards, or commercial networks. 4. Entered into an agreement with a company, Viacrypt, now Network Associates, to provide a fully compatible, low-cost commercial version of PGP. And that's required because a lot of companies require a commercial version before they will accept some kind of technology. So the PGP growth, it's grown explosively and is now widely used. A number of reasons can be cited for this growth. 1, it is available free worldwide in versions that run on a variety of platforms, including Windows, Unix, Macintosh, and many more. In addition, the commercial version satisfies users who want a product that come with vendor support. 2, it is based on algorithms that have survived extensive public review and are considered extremely secure. Specifically, the package includes RSA, DSS, and Diffie-Hellman for public key encryption, CAST-128 IDEA, and TripleDES for symmetric encryption, and SHA-1 for hash coding. 3, it has a wide range of applicability, from corporations that wish to select and enforce a standardized scheme for encrypting files and messages to individuals who wish to communicate securely with others worldwide over the internet and other networks. 4, it was not developed by, nor is it controlled by, any government or standards organization. For example, NSA, haha. For those with an instinctive distrust of the establishment, this makes PGP attractive. PGP is now on an Internet Standards Tract, RFC 3156, MIME security with OpenPGP. Nevertheless, PGP still has an aura of anti-establishment endeavor. So they're trying to be more of a people's product, an open product, as opposed to commercial or government controlled. And here's a summary of the PGP services. And the actual operation of PGP, as opposed to the management of keys, consists of 4 services: authentication, confidentiality, compression, and email compatibility, as shown in this figure. So take a moment, pause, and review this table. PGP authentication. The combination of SHA-1 and RSA provides an effective digital signature scheme. Because of the strength of RSA, the recipient is assured that only the possessor of the matching private key can generate the signature. Because of the strength of SHA-1, the recipient is assured that no one else could generate a new message that matches the hash code, and hence the signature of the original message. As an alternative, signatures can be generated using DSS SHA-1. Although signatures normally are found attached to the message or file that they sign, this is not always the case. Detached signatures are also supported. A detached signature may be stored and transmitted separately from the message it signs. This is useful in several contexts. A user may wish to maintain a separate signature log of all messages sent or received. A detached signature of an executable program can detect subsequent virus infection. Finally, detached signatures can be used when more than one party must sign a document, such as a legal contract. Each person's signature is independent and therefore applied only to the document. Otherwise, signatures would have to be nested, with the second signer signing both the document and the first signature, and so on. PGP confidentiality. Another basic service provided by PGP is confidentiality, which is provided by encrypting messages to be transmitted or to be stored locally in files. In both cases, the symmetric encryption algorithm CAST128 may be used. Alternatively, IDEA or TripleDES may be used. The 64-bit cipher feedback CFB mode is used. As always, one must address the problem of key distribution. In PGP, each symmetric key is used only once. That is, a new key is generated as a random 128-bit number for each message. Thus, although this is referred to in the documentation as a session key, it is in reality a one-time key. Because it is used only once, the session key is bound to the message and transmitted with it. To protect the key, it is encrypted with the receiver's public key. In the figure, it illustrates the sequence. As an alternative to the use of RSA for key encryption, PGP provides an option referred to as Diffie-Hellman. As was explained before, Diffie-Hellman is a key exchange algorithm. In fact, PGP uses a variant of Diffie-Hellman that does provide encryption-decryption known as EI-GAML. Several operations and observations may be made. First, to reduce encryption time, the combination of symmetric and public key encryption is used in preference to simply using RSA or EI-GAML to encrypt the message directly. CAST128 and the other symmetric algorithms are subsequently faster than RSA or EI-GAML. Second, the use of public key encryption solves the session key distribution problem, because only the recipient is able to recover the session key that is bound to the message. Note that we do not need a session key exchange protocol of the type discussed in Chapter 14 because we are not beginning an ongoing session. Rather, each message is a one-time independent event with its own key. Furthermore, given the store and forward nature of electronic mail, the use of handshaking to assure that both sides have the same session key is not practical. Finally, the use of a one-time symmetric key strengthens what is already a strong symmetric encryption approach. Only a small amount of plain text is encrypted with each key, and there is no relationship among the keys. Thus, to the extent that the public key algorithm is secure, the entire scheme is secure. To this end, PGP provides the user with a range of key size options from 768 to 3072 bits, which is the DSS key for signatures, and that is limited to 1024 bits. PGP confidentiality and authentication. As the figure illustrates, both services may be used for the same message. First, a signature is generated for the plaintext message and prepended to the message. Then the plaintext message plus signature is encrypted using CAST128 or IDEA or TripleDES, and the session key is encrypted using RSA or EI-GAML. This sequence is preferable to the opposite, encrypting the message and then generating a signature for the encrypted message. It is generally more convenient to store a signature with a plain text version of a message. Furthermore, for purposes of third-party verification, if the signature is performed first, a third party need not be concerned with the symmetric key when verifying the signature. In summary, when both services are used, the sender first signs the message with its own private key, then encrypts the message with a session key, and finally encrypts the session key with the recipient's public key. Let's talk about the compression. As a default, PGP compresses the message after applying the signature, but before encryption. This has the benefit of saving space both for email transmission and for file storage. The placement of the compression algorithm is critical. One, the signature is generated before the compression for two reasons. A, it is preferable to sign an uncompressed message so that one can store only the uncompressed message together with the signature for future verification. If one signed a compressed document, then it would be necessary either to store a compressed version of the message for later verification or to recompress the message when verification is required. B, even if one were willing to generate dynamically a recompressed message for verification, PGP's compression algorithm presents a difficulty. The algorithm is not deterministic. Various implementations of the algorithm achieve different trade-offs in running speed versus compression ratio, and as a result produce different compressed forms. However, these different compression algorithms are interoperable because any version of the algorithm can correctly decompress the output of any other version. Applying the hash function and signature after compression would constrain all PGP implementations to the same version of the compression algorithm. 2. Message encryption is applied after compression to strengthen cryptographic security. Because the compressed message has less redundancy than the original plaintext, cryptanalysis is more difficult. The compression algorithm used is zip, which is extremely popular, and that's described in Appendix G. PGP email compatibility. When PGP is used, at least part of the block is to be transmitted as encrypted. If only the signature service is used, then the message digest is encrypted with the sender's private key. If the confidentiality service is used, the message plus signature, if present, are encrypted with a one-time symmetric key. Thus, part or all of the resulting block consists of a stream of arbitrary 8-bit octets. However, many electronic mail systems only permit the use of blocks containing ASCII text. To accommodate this restriction, PGP provides the service of converting the raw 8-bit binary stream to a stream of printable ASCII characters. The scheme used for this purpose is radix 64 conversion. Each group of 3 octets of binary data is mapped into 4 ASCII characters. This format also appends a CRC to detect transmission errors. You can see an appendix for a description of this. The use of radix 64 expands a message by 33%. Fortunately, the session key and signature portions of the message are relatively compact, and the plaintext message has been compressed. In fact, the compression should be more than enough to compensate for the radix 64 expansion. For example, there's an average compression ratio of about 2.0 using zip. If we ignore the relatively small signature and key components, the overall effect of compression and expansion of a file of length x would be 1.33 times 0.5 times x equals an overall 0.66 times x. Thus, there is still an overall compression of about 1/3. One noteworthy aspect of the radix 64 algorithm is that it blindly converts the input stream to radix 64 format regardless of content, even if the input happens to be ASCII text. Thus, if a message is signed but not encrypted and the conversion is applied to the entire block, the output will be unreadable to the casual observer, which provides a certain level of confidentiality. As an option, PGP can be configured to convert to radix 64 format only the signature portion of the signed plaintext messages. This enables the human recipient to read the message without using PGP. PGP would still have to be used to verify the signature. So here we have a figure which illustrates the use of digital signature service provided by PGP. This is the digital signature scheme discussed and illustrated in figure 4.5 in chapter 4. To protect the key, it is encrypted with the receiver's public key. Figure 8.1b illustrates the sequence. As figure 8.1c illustrates, both services may be used for the same message. First, a signature is generated for the plaintext message and prepended to the message. Then the plaintext message plus signature is encrypted using CAST128 or IDEA or TripleDES, and the session key is encrypted using RSA or EI-GAML. The sequence is preferable to the opposite, encrypting the message and then generating a signature for the encrypted message. It is generally more convenient to store a signature with a plaintext version of a message. Furthermore, for purposes of third-party verification, if the signature is performed first, a third party need to not be concerned with the symmetric key when verifying the signature. In summary, when both services are used, the sender first signs the message with its own private key, then encrypts a message with a session key, and finally encrypts the session key with the recipient's public key. This figure shows the relationship among the four services so far discussed. On transmission, if it is required, a signature is generated using a hash code of the uncompressed plaintext. Then the plaintext plus signature, if present, is compressed. Next, if confidentiality is required, the block compressed plaintext or compressed signature plus plaintext is encrypted and prepended with the public key encrypted symmetric encryption key. Finally, the entire block is converted to radix 64 format. On reception, the incoming block is first converted back from radix 64 to binary. Then, if the message is encrypted, the recipient recovers the session key and decrypts the message. The resulting block is then decompressed. If the message is signed, the recipient recovers the transmitted hash code and compares it to its own calculation of the hash code. Secure Multi-Purpose Internet Mail Extension, S/MIME, is a security enhancement to the MIME Internet Email Format Standard based on technology from RSA Data Security. Although both PGP and S/MIME are an Internet on the IATF standards track, it appears likely that S/MIME will emerge as the industry standard for commercial and organizational use, while PGP will remain the choice for personal email security and for many users. S/MIME is defined in a number of different documents, most importantly RFCs 3370, 3850, 3851, and 3852. To understand S/MIME, we need to first have a general understanding of the underlying email format that it uses, namely MIME. But to understand the significance of MIME, we need to go back to the traditional email format standard RFC 822, which is still in common use. The most recent version of this format specification is RFC 5322, Internet Message Format. Accordingly, this section first provides an introduction to these two earlier standards and then moves on to a discussion of S/MIME. RFC 5322 defines a format for text messages that are sent using electronic mail. It has been a standard for internet-based text mail messages and remains in common use. In the RFC 5322 context, messages are viewed as having an envelope and contents. The envelope contains whatever information is needed to accomplish transmission and delivery. The contents compose the object to be delivered to the recipient. The RFC 5322 standard applies only to the contents. However, the content standard includes a set of header fields that may be used by the mail system to create the envelope, and the standard is intended to facilitate the acquisition of such information by programs. The overall structure of a message that conforms to RFC 5322 is very simple. A message consists of some number of header lines, the header, followed by unrestricted text, the body. The header is separated from the body by a blank line. Put differently, a message is ASCII text, and all lines up to the first blank are assumed to be the header and used by the user agent part of the mail system. A header line usually consists of a keyword, followed by a semicolon, followed by the keyword's arguments. The format allows a long line to be broken up into several special lines. The most frequently used keywords are from, to, subject, and date. Another field that is commonly found in RFC 5322 headers is message ID. This field contains a unique identifier associated with this message. Multi-Purpose Internet Mail Extension, MIME, is an extension to the RFC 5322 framework that is intended to address some of the problems and limitations of the use of Simple Mail Transfer Protocol, SMTP, defined in RFC 821, or some other mail transfer protocol and RFC 5322 for electronic mail. MIME is intended to resolve these problems in a manner that is compatible with existing 5322 implementations. The specification is provided in RFCs 2045 through 2049. The MIME specification includes the following elements. 1. 5 new message header fields are defined, which may be included in an RFC 5322 header. These fields provide information about the body of the message. 2. A number of content formats are defined, thus standardizing representations that support multimedia electronic mail. 3. Transfer encodings are defined that enable the conversion of any content format into a form that is protected from alteration by the email system. In this subsection, we introduce the 5 message header fields. The next 2 subsections deal with the content formats and transfer encodings. The 5 header fields defined in MIME are: MIME version must have the parameter value 1.0. This field indicates that the message conforms to RFCs 2045 and 2046. Content type describes the data contained in the body with sufficient detail that the receiving user agent can pick an appropriate agent or mechanism to represent the data to the user or otherwise deal with the data in an appropriate manner. Content transfer encoding indicates the type of transformation that has been used to represent the body of the message in a way that is acceptable for mail transport. Content ID, used to identify MIME entities uniquely in multiple contexts. Content description, a text description of the object with the body. That is useful when the object is not readable, for example, audio data. Any and all of the fields may appear in a normal RFC 5322 header. A compliant implementation must support the MIME version, content type, and content transfer encoding fields. The content ID and content description fields are optional and may be ignored by the recipient implementation. The bulk of the MIME specification is concerned with the definition of a variety of content types. This reflects the need to provide standardized ways of dealing with a wide variety of information representations in a multimedia environment. The table lists the content types defined in RFC 2046. There are 7 different major types of content and a total of 15 subtypes. In general, a content type declares the general type of data, and the subtype specifies a particular format for that type of data. For the text type of body, no special software is required to get the full meaning of the text aside from support of the indicated character set. The primary subtype is plain text, which is simply a string of ASCII characters or ISO 8859 characters. The enriched subtype allows greater formatting flexibility. The multi-part type indicates that the body contains multiple independent parts. The content type header field includes a parameter called a boundary that defines a delimiter between the body parts. This boundary should not appear in any parts of the message. Each boundary starts on a new line and consists of 2 hyphens followed by the boundary value. The final boundary, which indicates the end of the last part, also has a suffix of 2 hyphens. Within each part, there may be an optional ordinary MIME header. There are 4 subtypes of the multi-part type, all of which have the same overall syntax. The multi-part mixed subtype is used when there are a number of independent body parts that need to be bundled in a particular order. For the multi-part parallel subtype, the order of the parts is not significant. If the recipient system is appropriate, the multiple parts can be presented in parallel. For example, a picture or text part could be accompanied by a voice commentary that is played while the picture or text is displayed. For the multi-part alternative subtype, the various parts are different representations of the same information. The multi-part digest subtype is used when each of the body parts is interpreted as an RFC 5322 message with headers. This subtype enables the construction of a message whose parts are individual messages. For example, the moderator of a group might collect email messages from participants, bundle these messages, and send them out in one encapsulating MIME message. The message type provides a number of important capabilities in MIME. The message/RFC 822 subtype indicates that the body is an entire message, including header and body. Despite the name of this subtype, the encapsulated message may not only be a simple RFC 5322 message, but also may include MIME messages. The message partial subtype enables fragmentation of a large message into a number of parts, which must be reassembled at the destination. For this subtype, 3 parameters are specified in the content type: message/partial field, an ID common to all fragments, and the same message, a sequence number unique to each fragment, and the total number of fragments. The message external body subtype indicates that the actual data to be conveyed in this message are not contained in the body. Instead, the body contains the information needed to access the data. As with the other message types, the message external body subtype has an outer header and an encapsulated message with its own header. The only necessary field in the outer header is the content type field, which identifies this as a message or external body subtype. The inner header is the message of the header for the encapsulated message. The content type field in the outer header must include an access type parameter, which indicates the method of access, such as FTP, File Transfer Protocol. The application type refers to other kinds of data, typically either uninterpreted binary data or information to be processed by a mail-based application. The other major components of the MIME specification, in addition to content type specification, is a definition of transfer encodings for message bodies. The objective is to provide reliable delivery across the largest range of environments. The MIME standard defines 2 methods of encoding data. The content transfer encoding field can actually take on 6 values, as listed in the table. However, 3 of these values, 7-bit, 8-bit, and binary, indicate that no encoding has been done, but provide some information about the nature of the data. For SMTP transfer, it is safe to use the 7-bit form. The 8-bit and binary forms may be usable in other mail transport contexts. Another content transfer encoding value is X token, which indicates that some other encoding scheme is used for which a name is to be supplied. This could be a vendor-specific or application-specific scheme. The 2 actual encoding schemes defined are quoted printable and base 64. 2 schemes are defined to provide a choice between a transfer technique that is essentially human readable and one that is safe for all types of data in a way that is reasonably compact. The quoted printable transfer encoding is useful when the data consists of a large number of octets that correspond to printable ASCII characters. In essence, it represents non-safe characters by the hexadecimal representation of their code and introduces reversible soft line breaks to limit messages to 76 characters or less. The base 64 transfer encoding, also known as radix 64 encoding, is a common one for encoding arbitrary binary data in such a way as to be invulnerable to the processing by mail transport programs. It is also used in PGP and is described in an appendix. This figure, taken from RFC 2045, is the outline of a complex multi-part message. The message has 5 parts to be displayed serial: 2 introductory plain text parts, an embedded multi-part message, a rich text part, and a closing encapsulated text message in a non-ASCII character set. The embedded multi-part message has 2 parts to be displayed in parallel: a picture and an audio fragment. An important concept in MIME and SMIME is that of canonical form. A canonical form is a format appropriate to the content type that is standardized for use between systems. This is in contrast to native form, which is a format that may be peculiar to a particular system. This table from RFC 2049 should help clarify this matter. So pause and review this. In terms of general functionality, SMIME is very similar to PGP. Both offer the ability to sign and/or encrypt messages. In this subsection, we briefly summarize SMIME capability. We then look at more detail of this capability by examining message formats and message preparation. SMIME provides the following functions: enveloped data. This consists of encrypted content of any type and encrypted content encryption keys for one or more recipients. Signed data. A digital signature is formed by taking the message digest of the content to be signed and then encrypting that with the private key of the signer. The content plus signature are then encoded using base64 encoding. A signed data message can only be viewed by a recipient with SMIME capability. Clear signed data. As with signed data, a digital signature of the content is formed. However, in this case, only the digital signature is encoded using base64. As a result, recipients without SMIME can view the message content, although they cannot verify the signature. Signed and envelope data. Signed only and envelope data entities may be nested so that encrypted data may be signed and signed data or clear signed data may be encrypted. This table summarizes the cryptographic algorithms used in SMIME. SMIME uses the following terminology taken from RFC 2119. Keywords for use in RFCs to indicate requirements level. To specify the requirement level. Must. The definition is an absolute requirement of the specification. An implementation must include this feature or function to be in conformance with the specification. Should. There may exist valid reasons in particular circumstances to ignore this feature or function, but it is recommended that an implementation include this feature or function. SMIME incorporates 3 public key algorithms. The Digital Signature Standard, DSS, described in Chapter 3, is the preferred algorithm for digital signature. SMIME lists Diffie-Hellman as the preferred algorithm for encrypting session keys. In fact, SMIME uses a variant of Diffie-Hellman that does not provide encryption-decryption, known as E1-GAML. As an alternative, RSA, described in Chapter 3, can be used for both signatures and session key encryption. These are the same algorithms used in PGP and provide a high level of security. For the hash function used to create the digital signature, the specification requires the 160-bit SHA-1, but recommends receiver support of the 128-bit MD5 for backward compatibility with older versions of SMIME. As we discussed in Chapter 3, there is justifiable concern about the security of MD5, so SHA-1 is clearly the preferred alternative. For message encryption, 3-key triple DES is recommended, but compliant implementations must support 40-bit RC2. The latter is a weak encryption algorithm, but allows compliance with US export controls. The SMIME specification includes a discussion of the procedure for deciding which content encryption algorithms to use. In essence, a sending agent has 2 decisions to make. First, the sending agent must determine if the receiving agent is capable of decrypting using a given encryption algorithm. Second, if the receiving agent is only capable of accepting weakly encrypted content, the sending agent must decide if it is acceptable to send using weak encryption. To support this decision process, a sending agent may announce its decrypting capabilities in order of preference for any message that it sends out. A receiving agent may store that information for future use. So here's a table of SMIME content types. SMIME makes use of a number of new MIME content types, which are shown in the table. All of the new application types use the designation PKCS. This refers to a set of public key cryptographic specifications used by RSA laboratories and made available for the SMIME effort. Securing a MIME entity. SMIME secures a MIME entity with a signature, encryption, or both. A MIME entity may be an entire message, except for the headers, or if the MIME content is multi-part, then a MIME entity is one or more of the subparts of the message. The MIME entity is prepared according to the normal rules for MIME message preparation. Then the MIME entity plus some security-related data, such as algorithm identifiers and certificates, are processed by SMIME to produce what is known as a PKCS object. A PKCS object is then treated as a message content and wrapped in MIME, provided with appropriate MIME headers. This process should become clear as we look at some specific objects and provide some examples. In all cases, the message to be sent is converted to canonical form. In particular, for a given type and subtype, the appropriate canonical form is used for the message content. For a multi-part message, the appropriate canonical form is used for each subpart. The use of transfer encoding requires special attention. For most cases, the result of applying the security algorithm will be to produce an object that is partially or totally represented in arbitrary binary data. This will then be wrapped in an outer MIME message, and transfer encoding can be applied at that point, typically base 64. However, in the case of a multi-part signed message, described in more detail later, the message content in one of the subparts is unchanged by the security process. Unless that content is 7-bit, it should be transfer encoded using base 64 or quotable printable so that there's no danger of altering the content to which the signature was applied. Envelope data. An application /PKCS7-MIME subtype is used for one of 4 categories of SMIME processing, each with a unique SMIME type parameter. In all cases, the resulting entity, referred to as an object, is represented in a form known as Basic Encoding Rules, BER, which is defined in ITU-T Recommendation X.209. The BER format consists of arbitrary octet strings, is therefore binary data. Such an object should be transfer encoded with base 64. In the outer MIME message, we first look at enveloped data. The steps for preparing an enveloped data MIME entity are: 1. Generate a pseudorandom session key for a particular symmetric encryption algorithm, RC2/40 or SSS. 2. For each recipient, encrypt the session key with the recipient's public RSA key. 3. For each recipient, prepare a block known as recipient info that contains an identifier of the recipient's public key certificate, an identifier of the algorithm used to encrypt the session key, and the encrypted session key. 4. Encrypt the message content with the session key. The recipient info blocks followed by the encrypted content constitute the enveloped data. This information is then encoded into base 64. To recover the encrypted message, the recipient first strips off the base 64 encoding. Then the recipient's private key is used to recover the session key. Finally, the message content is decrypted with the session key. Sign data. The sign data SMIME type can be used with one or more signers. For clarity, we confine our description to the case of a single digital signature. The steps for preparing a signed data MIME entity are: 1. Select a message digest algorithm, SHA or MD5. 2. Compute the message digest hash functions of the content to be signed. 3. Encrypt the message digest with the signer's private key. 4. Prepare a block known as signer info that contains the signer's public key certificate, an identifier of the message digest algorithm, an identifier of the algorithm used to encrypt the message digest, and the encrypted message digest. The signed data entity consists of a series of blocks including a message digest algorithm identifier, the message being signed, and signer info. The signed data entity may also include a set of public key certificates sufficient to constitute a chain from a recognized root or top-level certification authority to the signer. This information is then encoded into base 64. To recover the signed message and verify the signature, the recipient must first strip off the base 64 encoding. Then the signer's public key is used to decrypt the message digest. The recipient independently computes the message digest and compares it to the decrypted message digest to verify the signature. Clear signing. Clear signing is achieved using the multi-part content type with a signed subtype. As was mentioned, the signing process does not involve transforming the message to be signed so that the message is sent in the clear. Thus, recipients with MIME capability, but not SMIME capability, are able to read the incoming message. A multi-part signed message has two parts. The first part can be any MIME type, but must be prepared so that it will not be altered during transfer from source to destination. This means that if the first part is not 7-bit, then it needs to be encoding using base 64 or quoted printable. Then this part is processed in the same manner as signed data, but in this case an object with signed data format is created that has an empty message content field. This object is a detached signature. It is then transfer encoded using base 64 to become the second part of the multi-part signed message. This second part has a MIME content type of application and a subtype of PKCS7-signature. SMIME certificate processing. SMIME uses public key certificates that conform to version 3 of the X509. See Chapter 4. The key management scheme used by SMIME is in some ways a hybrid between a strict X509 certificate hierarchy and PGP's web of trust. As with the PGP model, SMIME managers and/or users must configure each client and with certificate revocation lists. That is, the responsibility is local for maintaining the certificates needed to verify incoming signatures and to encrypt outgoing messages. On the other hand, the certificates are signed by certification authorities. User agent role. An SMIME user has several key management functions to perform. Key generation. The user of some related administrative utility, one associated with LAN management, must be capable of generating separate Diffie-Hellman and DSS key pairs and should be capable of generating RSA key pairs. Each key pair must be generated from a good source of non-deterministic random input and be protected in a secure manner. A user agent should generate RSA key pairs with length in the range of 768 to 1024 bits and must not generate a length of less than 512. Registration. A user's public key must be registered with a certification authority in order to receive an X509 public key certificate. Certificate storage and retrieval. A user requires access to a local list of certificates in order to verify incoming signatures and to encrypt outgoing messages. Such a list could be maintained by the user or some local administrative entity on behalf of a number of users. VeriSign certificates. There are several companies that provide certification authority CA services. For example, Nortel has designated an enterprise CA solution and can provide SMIME support within an organization. There are a number of internet-based CAs, including VeriSign, GTE, the U.S. Postal Service, etc. Of these, the most widely used is the VeriSign CA service, a brief description of which we now provide. VeriSign provides a CA service that is intended to be compatible with SMIME and a variety of other applications. VeriSign issues X509 certificates with the product name VeriSign Digital ID. As of early 1998, over 35,000 commercial websites were using VeriSign service digital IDs, and over 1 million consumer digital IDs had been issued to users of Netscape and Microsoft browsers. The information contained in a digital ID depends on the type of digital ID and its use. At a minimum, each digital ID contains the following: owner's public key, owner's name or alias, expiration date of the digital ID, serial number of the digital ID, name of the certification authority that issued the digital ID, digital signature of the certification authority that issued the digital ID. Digital IDs can also contain other user-supplied information, including address, email address, basic registration information, country, zip code, age, and gender. So here's a table of VeriSign public key certificate classes. VeriSign provides 3 levels or classes of security for public key certificates, as summarized in the table. A user requests a certificate online at VeriSign's website or other participating websites. Class 1 and Class 2 requests are processed online and in most cases take only a few seconds to approve. Briefly, the following procedures are used. For Class 1 digital IDs, VeriSign confirms the user's email address by sending a PIN and digital ID pickup information to the email address provided in the application. For Class 2 digital IDs, VeriSign verifies the information in the application through an automated comparison with a consumer database, in addition to performing all the checking associated with a Class 1 digital ID. Finally, confirmation is sent to the specified postal address, alerting the user that a digital ID has been issued in his or her name. For Class 3 digital IDs, VeriSign requires a higher level of identity assurance. An individual must prove his or her identity by providing notarized credentials or by applying in person. Enhanced security services. As of this writing, 3 enhanced security services have been proposed in an internet draft. The details of these may change and additional services may be added. The 3 services are: 1. Signed receipts. A signed receipt may be requested in a signed data object. Returning a signed receipt provides proof of delivery to the originator of a message and allows the originator to demonstrate to a third party that the recipient received the message. In essence, the recipient signs the entire original message plus the original sender's signature and appends the new signature to form a new SMIME message. 2. Security labels. A security label may be included in the authenticated attributes of a signed data object. A security label is a set of security information regarding the sensitivity of the content that is protected by SMIME encapsulation. The labels may be used for access control by indicating which users are permitted access to an object. Other uses include priority, secret, confidential, restricted, and so on, or role-based, describing which kind of people can see the information. For example, patient's healthcare team, medical billing agents, etc. Secure mailing lists. When a user sends a message to multiple recipients, a certain amount of per recipient processing is required, including the use of each recipient's public key. The user can be relieved of this work by employing the services of an SMIME mail list agent, MLA. An MLA can take a single incoming message, perform the recipient specified encryption for each recipient, and forward the message. The originator of a message need only send the message to the MLA with encryption performed using the MLA's public key. Domain keys, identified mail, DKIM. This is used by Google. Domain keys, identified mail, is a specialized form of cryptographic signing for email messages permitting a signing domain to claim responsibility for a message in the stream. Message recipients or agents acting on their behalf can verify the signature by querying the signer's domain directly to receive the appropriate public key, and thereby can confirm the message was attested to by a party in possession of the private key for signing domain. DKIM is a proposed internet standard, RFC 4871, Domain Keys Identified Mail, DKIM signatures. DKIM has been widely adopted by a range of email providers, including corporations, government agencies, Gmail, Yahoo, and many internet service providers. Here's a figure. Function modules and standardized protocols used between them. To understand the operation of DKIM, it is useful to have a basic grasp of the Internet Mail architecture, which is currently defined in RFC 5598. This subsection provides an overview of the basic concepts. At its most fundamental level, the Internet Mail architecture consists of a user world in the form of message user agents, MUAs, and the transfer world in the form of message handling service, MHS, which is composed of message transfer agents, MTA. The MSH accepts a message from one user and delivers it to one or more other users, creating a virtual MUA to MUA exchange environment. This architecture involves three types of interoperability. One is directly between users. Messages must be formatted by the MUA on behalf of the message author so that the message can be displayed to the message recipient by the destination MUA. There are also interoperability requirements between the MUA and the MSH. First, when a message is posted from an MUA to the MSH, and later when it's delivered from the MHS to the destination MUA. And then it goes to the MHS, and later when it is delivered from the MHS to the destination MUA. Interoperability is required among the MTA components along the transfer path through the MHS. The figure illustrates the key components of the Internet Mail architecture, which include the following. Message User Agent, MUA, operates on behalf of user actors and user applications. It is their representative within the email service. Typically, this function is housed in the user's computer and is referred to as a client email program or a local area network email server. The author MUA formats a message and performs initial submission into the MHS via a MSA. The recipient MUA process receives mail and stores and displays it to the recipient user. Mail Submission Agent, MSA, accepts the message submitted by an MUA and enforces the policies of the hosting domain and the requirements of the Internet standards. This function may be located together with the MUA or as a separate functional model. In the latter case, the Simple Mail Transfer Protocol, SMTP, is used between the MUA and the MSA. Message Transfer Agent, MTA, realize mail for one application level hop. It is like a packet switch or an IP router in that its job is to make routing assessments and to move the message closer to the recipients. Relaying is performed by a sequence of MTAs until the message reaches a final destination MDA. An MTA also adds trace information to the message header. SMTP is used between MTAs and between an MTA and an MSA or MDA. Mail Delivery Agent, MDA, responsible for transferring the message from the MSH to the MS. Message store, MS. An MUA can employ a long-term MS. An MS can be located on a remote server or the same machine as the MUA. Typically, an MUA retrieves messages from a remote server using POP, Post Office Protocol, or IMAP, Internet Message Access Protocol. Two other concepts need to be defined. An administrative management domain, ADMD, is an internet email provider. Examples include a department that operates a local mail relay, MTA, an IT department that operates an enterprise mail relay, and an ISP that operates a public shared email service. Each ADMD can have different operating policies and trust-based decision-making. One obvious example is the distinction between mail that is exchanged within an organization and mail that is exchanged between independent organizations. The rules for handling the two types of traffic tend to be quite different. The domain name system, DNS, is a directory lookup service that provides a mapping between the name of a host on the internet and its numerical address. Email threats. RFC 4686 characterizes the range of attackers on a spectrum of 3 levels of threat. 1. At the low end are attackers who simply want to send email that a recipient does not want to receive. The attacker can use one of a number of commercially available tools that allow the sender to falsify the origin address of messages. This makes it difficult for the receiver to filter spam on the basis of originating address or domain. 2. At the next level are professional senders of bulk spam mail. These attackers often operate as commercial enterprises and send messages on behalf of third parties. They employ more comprehensive tools for the attack, including mail transfer agents, MTAs, and registered domains and networks of compromised computers, zombies, to send messages and, in some cases, to harvest addresses to which to send. The most sophisticated and financially motivated senders of messages are those who stand to receive substantial financial benefit, such as from an email-based fraud scheme. These attackers can be expected to employ all of the above mechanisms and additionally may attack the internet infrastructure itself, including DNS cache poisoning attacks and IP routing attacks. So here we have a figure. It's a simple example of DKIM deployment. DKIM is designed to provide an email authorization technique that is transparent to the end user. In essence, a user's email message is signed by a private key of the administrative domain from which the email originates. The signature covers all of the content of the message and some of the RFC 5322 message headers. At the receiving end, the MDA can access the corresponding public key via a DNS and verify the signature, thus authenticating that the message comes from the claimed administrative domain. Thus, mail that originates from somewhere else but claims to come from a given domain will not pass the authentication test and can be rejected. This approach differs from that of SMIME and PGP, which uses the originator's private key to sign the content of the message. The motivation for DKIM is based on the following reasoning. 1. SMIME depends on both the sending and receiving users. Employing SMIME for almost all users, the bulk of incoming mail does not use SMIME, and the bulk of mail the user wants to send is to recipients not using SMIME. 2. SMIME signs only the message contents. Thus, RFC 5322 header information concerning origin can be compromised. 3. DKIM is not implemented in client programs, MUAs, and is therefore transparent to the user. The user need take no action. DKIM applies to all mail from cooperating domains. DKIM allows good senders to prove that they did send a particular message and to prevent forgers from masquerading as good senders. Figure 8.5 is a simple example of the operation of DKIM. We begin with a message generated by a user and transmitted into the MHS to an MSA that is within the user's administrative domain. An email message is generated by an email client program. The content of the message plus selected RFC 5322 headers is signed by the email provider using the provider's private key. The signer is associated with a domain, which could be a corporate local network, an ISP, or a public email facility such as Gmail. The signed message then passes through the internet via a sequence of MTAs. At the destination, the MTA retrieves the public key for the incoming signature and verifies the signature before passing the message on to the destination email client. The default signing algorithm is RSA with SHA-256. RSA with SHA-1 also may be used. So here we have a figure. It's DKIM functional flow. The figure provides a more detailed look at the elements of DKIM operation. Basic message processing is divided between a signing administrative management domain, ADMD, and a verifying ADMD. At its simplest, this is between the originating ADMD and the delivering ADMD, but it can involve other ADMDs in the handling path. Signing is performed by an authorized module within the signing ADMD and uses private information from a key store. Within the originating ADMD, this might be performed by the MUA, MSA, or MTA. Verifying is performed by an authorized module within the verifying ADMD. Within a delivering ADMD, verifying might be performed by an MTA, MDA, or MUA. The module verifies the signature or determines whether a particular signature was required. Verifying the signature uses public information from the key store. If the signature passes, reputation information is used to assess the signer, and that information is passed to the message filtering system. If the signature fails, or there is no signature using the author's domain, information about signing practices related to the author can be retrieved remotely and/or locally, and that information is passed to the message filtering system. For example, if the sender, for example, Gmail, uses DKIM but no DKIM signature is present, then the message may be considered fraudulent. The signature is inserted into the RFC 5322 message as an additional header entry, starting with the keyword DKIM signature. You can view examples from your own incoming mail by using the View Long Headers or similar wording option for an incoming message. Before a message is signed, a process known as canonicalization is performed on both the header and the body of the RFC 5322 message. Canonicalization is necessary to deal with the possibility of minor changes in the message made en route, including character encoding, treatment of trailing white space in the message lines, the folding and unfolding of header lines. The intent of canonicalization is to make a minimal transformation on the message for the purpose of signing. The message itself is not changed. Canonicalization must be performed again by the verifier that will give its best chance of producing the same canonical value at the receiving end. DKIM defines two header canonicalization algorithms, simple and relaxed, and two for the body with the same names. The simple algorithm tolerates almost no modification, while the relaxed tolerates common modifications. The signature includes a number of fields. Each field begins with a tag consisting of a tag code followed by an equal sign and ends with a semicolon. Summary: pretty good privacy, domain keys, identified mail, and SMIME. We've covered it all, so we are really good at security with email. Thanks for listening, and bye for now.